move to the last speaker of the session, Robert Shmookler-Reis from Fayetteville, US. So he's going to talk about aspirin, the oldest new anti-aging drug.
Thank you very much. Well, I'd like to begin, everybody begins by thanking Aubrey, but I want to thank him not so much for inviting me as for the hard work he does. He's done an amazing job putting together this really wonderful project. I think he's not here, so he won't be embarrassed. So today I want to tell you about a drug that you all probably think you know everything about, because aspirin's been around for over 100 years. And we all know its primary mode of action is as a COX inhibitor. Unlike all the second and third generation COX inhibitors, it's not specialized for COX-2. It's a generalized COX-1 and COX-2 inhibitor. It doesn't avoid some of the side effects of the pure COX-2 inhibitors, but it's really very, very good at preventing at inhibiting COX conversion of arachidonic acid into the prostaglandins, which are pro-inflammatory and also mediate platelet aggregation. So the clinical benefits of aspirin were only fully realized in terms of large population studies when, I think, beginning with the physician's health study, but then there have been a total of 6 really rather large-scale clinical trials to look for the overall benefits, so you could actually weigh the gains versus the costs. And a meta-analysis of 6 such studies showed, rather interestingly, that aspirin, in addition to its prevention of cardiovascular disease, which it was very good for and fully validated as expected, and it also reduced stroke, it also reduced cancer and a whole variety of different adult age-dependent onset cancers were reduced in their incidence by aspirin treatment. This is just taking low-dose aspirin, typically 81 milligrams a day, or the 325 milligrams every other day in different studies. But in addition, it has benefits for diabetes. It has some benefits for delaying but not altering the severity of Alzheimer's. It looked like almost a panacea. That's the Greek word for a drug that cures everything. But it's not quite everything. Everything that it cures, the things that it's good for, are all age-dependent. And it was shown to have a remarkably unforeseen effect on total cause of mortality, even if you removed all the known disease effects, specific disease effects. The other causes of death had exactly the same overall risk factor reduction. So it wasn't quite significant in this first meta-analysis, P of 0.08. It doesn't mean it wasn't real. In a study of specifically diabetics, to demonstrate its benefits to diabetics in aiding and abetting or ameliorating diabetes, it also reduced all-cause mortality there. That was significant, with the greatest effect in men. If you look at mice in a controlled study where where aspirin was administered at 3 different sites, 3 different universities, looking at a whole range of candidate genes in an 8-way cross, so you have some genetic heterogeneity in the mouse population. The improvement due to aspirin, now in this very genetically homogeneous and homogeneous environment population of mice, you can't quite achieve that with people, is now much more significant, but the size of the effect is about the same. It's about an 8% extension of lifespan and specific to male mice. So the question remains unresolved. Is aspirin really just having a bunch of disease-specific benefits, through its diverse activities, and those coincidentally all add up to more than the known ones because there are some other specific diseases? Or is it actually affecting the underlying common factor that these age-dependent diseases share, which is they're age-dependent? Aging is the common factor. So it occurred to us that it's possible that aspirin is anti-aging. And so we administered low-dose aspirin equivalent dose to a nematode, C. elegans. And you've seen pictures of C. elegans. You know they're little 1 millimeter long worms. They don't have a heart, so we don't have to worry about cardiovascular mode of action, and they don't get cancer. So, and they don't, as far as we know, get Alzheimer's, although I don't think they remember things very well anyway. Okay. So, rather to our surprise, when these are the control worms. They live an adult lifespan of about 17 days at 20 degrees. And when we gave either of 2 doses of aspirin, we extended their lifespan by between 20 and 28% in 4 different experiments. So this is highly reproducible, and it's a much bigger effect than we saw in humans or mice. But it also, rather interestingly, you got about 2/3 as good of an effect in multiple experiments with salicylate. Now, salicylate is the stuff you can get in a cream to rub on arthritic joints. It's basically aspirin without the acetyl group. So it's no longer an acetyl donor, but it's still anti-inflammatory. So you do see a postponement of aging and an increase in lifespan with aspirin and salicylate. For reasons I'll get to in a little bit, we suspected that aspirin may be acting through the insulin-like signaling pathway. Basically, we did transcriptomics with a targeted set of genes, and it looked like the insulin-like signaling pathway was being inhibited. So the insulin-like signaling pathway is kind of a gun, the smoking end of which is a transcription factor. In mammals, it's called FOXO. In C. elegans, it's DAF16. And there's a DAF16 defective mutant in C. elegans. So we used that mutant and treated it with aspirin. So here you can see the wild type in green, the aspirin-treated worms. It's a different experiments, a slightly different increase here, in red. But the 2 curves that virtually superimpose are the DAF16 mutant plus and minus aspirin. So in other words, if you don't have that smoking end of the gun, if you don't have that transcription factor, FOXO, then aspirin does you no good at all. That doesn't tell you, by the way, it does not mean that insulin-like signaling is necessarily the only or the pathway of action, because there are other pathways, including junk signaling, AMPK, that also converge on this same transcription factor. So what we next looked at was whether we could, in fact, see a slowing of the aging process, looking at all the best known biomarkers of the aging process in C. elegans. You can't look at a C. elegans and tell how old it is. It's not like people, but there are a number of measures that are very reliable parameters that covary with aging. One of them is the generation of Ross. It normally increases with age. And here we simply show that if you expose a normal worm, a wild-type worm, to dichlorofluorocene diacetate, which is a pro-fluorogenic precursor that in the presence of Ross is converted to a fluorescent compound, that you see quite a bit of fluorescence as the worm ages. This is a middle-aged worm. The same aged worm treated with aspirin for the preceding 3 days has about 40% less fluorescence. Salicylic acid does just as well. And that's a highly reproducible result. So generation of Ross is attenuated by aspirin. As you might expect, therefore, the sensitivity of the worms to killing biperoxide, which basically creates an oxidative challenge. I might add that I know that chemically, even though you will get a burst of ROS with hydrogen peroxide treatment, the biggest effect is a lipoperoxidation cascade, which is induced by peroxide treatment. But that's also the only free radical chain reaction that our cells are exposed to, so it's actually a rather good model stress. And this is the killing curve in time for 5 millimolar hydrogen peroxide for just normal worms untreated. And if you treat them with aspirin, they get about a 15% protection. And salicylate, again, is somewhat intermediate. Another marker that's been shown, and here I actually do show the age regression to change with age, is the pharyngeal pumping or feeding rate. The worm has one of its biggest muscles is its pharynx, which it uses to basically pump food into its gut. And the rate of pharyngeal pumping is an extremely reliable biomarker of the age of the worm. As it gets older, it pumps less and less. It loses its appetite. This is the curve for untreated worms as a function of age, showing just points at day 4, 8, 12, and 16. So just for reference, day 16 is just a little past the midpoint for mortality of adult age. And either aspirin or salicylate, and in this they are interchangeable, gives a postponement of that decline. You could see it as pushing it to the right, or you could see it as pushing it up. Either way, it's a benefit. Another biomarker, or actually a pair of biomarkers, is motility. And the two things you're going to see on this are the red bars, which show movement in response to touch. So that's responsive movement. And the purplish blue bars show spontaneous movement. So the first thing to note is that by the time the worm's gone to age 12, which is a little more than half of its lifespan, of its median lifespan, it's lost most spontaneous movement. They're doing, this is the percent of worms that are moving in a snapshot of the worms. So it doesn't mean that they never move. It's just that the movement, which would be at about 40% in young worms, is already down considerably by day 12, and it's almost down to 0 by day 16. So they will move when they're prodded, though, and that clearly is a parameter that is not terribly impaired by day 12, is somewhat worse by day 16, and aspirin can't do much for that. It does something for the spontaneous movement, though. You get about a doubling of the spontaneous movement. And here, what I'd like you to focus on is what actually deteriorated between day 12 and day 16. So the control has gone down 35% in its movement in response to touch. And the aspirin and salicylate treated worms have only gone down 4% and 7% respectively. So the point is that the age-dependent loss of responsive movement is especially spared, but so is the spontaneous movement. The last measure we looked at is protein aggregation. And for this, we couldn't use wild-type worms. We used a very convenient model of neurodegenerative diseases in which a string of 40 glutamines, we call it Q40, the amino acid code for glutamine, in fusion with YFP, yellow fluorescent protein. And the same amount of this protein is made in all of these pictures. It's just that at the sensitivity of photography, you don't see the diffuse YFP very well. There's a cell in which you can sort of see it diffuse. It's not aggregated. But when it aggregates, it forms very bright spots that increase in number and intensity with age. They're an extremely reliable biomarker of worm aging, although they don't change nearly as fast after age about 8 days as they do before. This is a 6-day-old worm, so it's still in the transition phase, and at 2 different magnifications you can see that untreated there's quite a bit of aggregate formation, and the number of aggregates in the aspirin-treated worms has gone down about 22%. The intensity of each aggregate and the area of the aggregates themselves are down quite a bit. So the total aggregate intensity that you would see is down more than 50%. It's rather impressive visually. If you just look at one of those dimensions, it's not quite as impressive. But the point is that aspirin is very good at reducing this aggregation of proteins, which certainly is responsible for neurodegenerative diseases, and in the view of scientists like Rick Morimoto, may have a lot to do with other aging deficits. So how does it work? Well, these are genes, the superoxide dismutase genes. There are 3 of them, and 3 catalases in C. elegans that are activated by DAF16 when it's not been inhibited by insulin-like signaling. So blocking insulin-like signaling activates these, and you can see that they're further activated by treatment with salicylate and even more by aspirin. And these are significant, especially for catalase 2 and 3 and SODS 2 and 3. JNK is a stress response kinase. It also intersects by activating DAF16 for those pro-longevity genes. And it's almost 4-fold stimulated by aspirin quite reproducibly. INT7 activates the insulin-like signaling pathway. It's an agonist, so you wouldn't want more of that because that insulin-like signaling pathway blocks DAF16's entry into the nucleus. And you actually see a 30% reduction here. Whereas here's the only place we found where salicylic acid is different from aspirin, it actually increases it. So this is just to put everything into context. Aspirin is blocking INT7, so it's reducing activation of the insulin-like signaling pathway. That pathway leads to DAF16 being phosphorylated and excluded from the nucleus. So this should really be an inhibitory bar here. JNK activates DAF16 and it makes it more active going into the nucleus. So JNK is upregulated, this pathway is downregulated. One other thing that we looked at to answer the question, why is aspirin more effective than salicylate? The only difference between them being the acetyl moiety. Aspirin is a potent acetylating agent. It acetylates about 20% of mitochondrial proteins and a slightly smaller percentage of non-mitochondrial proteins in cells. So here is a Western blot where we've actually just blotted total protein, but we've probed with antibody to acetyllysine, and you can see acetyl groups increased in the aspirin-treated lane over the control lane. That's very reproducible. It's a several-fold increase, but it's not for every protein. This protein doesn't change. This protein doesn't change much. That one does also. But these all change quite a bit. At the same time, we looked at the same protein for phosphorylation. And the way we did that is with a phosphoprotein-sensitive stain. But you can see that phosphorylation is decreased by aspirin treatment. Why should that be? Well, it could be a simple byproduct of acetylation. Given multiple sites of acetylation, some of those will be close enough to sites of phosphorylation to simply sterically block them. We don't know that that's the mechanism. We're looking further into this. But since phosphorylation is the key to most of the signaling cascades that I showed you on the last slide, attenuating phosphorylation will somewhat reduce signaling. Why would you want to reduce signaling? Well, I'll just remind you without a slide to show you that as we discovered in 2008, a nematode mutant in the AGE1 PI3 kinase that basically makes none of it at all, it's a truncation mutant, in the second homozygous generation was 10 times as long as normal. And it has, when we looked at its transcriptional profile, it silenced essentially all of the signaling pathways. Not quite all of them, but most of the signaling pathways. So it doesn't want to know. It basically, in a benign environment, does better without being responsive to its environment. And in a way, aspirin may be emulating that. So conclusions, aspirin retards the aging process in nematodes, mice and men, at least that all the data are consistent with that conclusion. In C. elegans, all of the life extension depends on this transcription factor, DAF16-FOXO. And when you treat with aspirin, insulin-like signaling, that means in the worm it's only one pathway that is about equidistant from our insulin signaling pathway and IGF-1 pathway. It's reduced, but junk-mediated stress signaling is increased by aspirin. That's it. I'll be glad to take questions, but first I'd like to acknowledge the people who did the work. My right-hand man, Srinivas Ayyadevara, is a colleague I've worked with for a long time. Jay Mehta is a cardiologist who actually introduced me to aspirin. And Chongpeng Hu, or Hu Chongpeng, and Mohammed Khaidakov also, and Sonu Mitra did some of the work. Thank you very much.
Thank you very much for a very interesting report on a very interesting item. Can you somehow compare the effect of aspirin to that of other anti-inflammatory substances such as ibuprofen maybe? You know, there was a report recently that ibuprofen prevents Parkinson's disease.
Right. So ibuprofen is one of the COX-2 specialized later generation drugs that really is a follow-on from aspirin. And interestingly, it's more effective than aspirin for Parkinson's, but less effective for Alzheimer's. Clearly, each of these drugs has its own spectrum. We have tried a variety of non-aspirin anti-inflammatory drugs in the worm. None of them is as effective as aspirin. So,
yeah, we can take two questions.
So, you are probably the most knowledgeable person.
I don't think that's on. I want everybody to hear what you're saying about me.
Hello? Okay, hi. You are perhaps the most knowledgeable person with the deepest insight into almost all these subjects that I have ever encountered, so I am reluctant to disagree with you on the interpretation of a study. But going back to the NTP result, I think if you break that down further, what you see is there's really a very marginal effect, if any, at 2 of the 3 sites. There's only one site where there is a significant effect on lifespan, and that's the site where you have the shortest lifespan in the first place. So I suggest that that is likely a case where you've just got poor animal husbandry. You're more effectively normalizing the curve, as has been seen with all kinds of antioxidants and garbage that doesn't actually extend life. And similarly, when you've got a meta-analysis of 6 studies and you show a non-significant effect, I suggest that's a non-significant effect.
You suggest that non-significant is non-significant.
Exactly. Yes.
I think in the context of the other studies, you know, all that the magic p-value of 0.05 means is that we have decided to arbitrarily set our standards, set our barriers at a 5% chance of something like this happening at random if there were no effect. It doesn't mean the effect's not there.
I think it should be a tighter standard than that.
Yeah, well, I won't disagree with you. I won't disagree at all. And so one of the grants we proposed is, in fact, to do a much more careful, what's called self-control study, where it's a block design where you add aspirin after you've established a baseline. And I don't know if we'll get funded for it, but I think that the problem is that when so much money has been invested in all the studies that have been done on tens of thousands of people, it's very hard to persuade grant funding bodies that another one should be done.
A comment and a question. If I understand the pharyngeal pumping, they're eating more and not living less. Second, with aspirin. Second, what about the acetylation of histones?
Okay, 2 very good points. Okay, the first point is that when we looked at pharyngeal pumping, the worms are clearly spared the decline in pharyngeal pumping of wild-type worms so when they're exposed to aspirin. So they're eating more than their untreated controls. That proves that it's not acting by caloric restriction, right? The improvement would be perhaps, I think unarguably, would be somewhat greater if it weren't that they were less calorically inhibited when they have aspirin. But that is an age-dependent decline and ultimately is bad for the worm because it will ingest less than it needs to continue survival.
Do you take aspirin?
Oh, I wish you hadn't asked me that. My wife does. I used to take aspirin, and for the same reason that other aspirin takers have in these trials abandoned it, I get ulcer-like symptoms after a couple of weeks. So I may try it again as an alternate day therapy, but I'm not taking it now. So take everything with that grain of salt.
In your C. elegans experiments, you've used a dose of 1 millimolar. I mean, it's going into the same direction. This would be quite a huge dose for a human, 1 millimolar. So what doses do you suggest? I mean, we have everything from 100 milligram up to where do we expect to have to become significancy?
This is a very perceptive question, and the worm is not a person, and the doses that are needed for effective dose in the worm depend on its uptake and degradation of whatever you give. So there's no way to know. It's hard enough to get a correspondence between mice and humans. From worms to humans, all bets are off. But I have to tell you that the experiments that we did, this is unpublished work that is still in progress. The initial experiments were all done with 1 millimolar aspirin, and then we more recently did a set with a range of doses of aspirin, 0.5 millimolar, 1 millimolar, 2 millimolar, and the very best was a 0.5 millimolar. So we obviously have to go lower. I don't know what the optimal dose is even for the worm at this point.
Could it be that the increased pharyngeal pumping leads to a shorter bowel transit time, and as a consequence of that, caloric restriction? Have you studied that?
We haven't, and there is a way to do it because
yes, of course.
Dr. Thomas in Seattle does a fecal deposit study where he actually looks at the end product of digestion, and so you can get some idea of the periodicity of that. But no, I know that pharyngeal pumping rate declines with age and is a good biomarker of the age of the worms. I don't know what it translates to in terms of metabolism.
So with your average lifespan extension was quite substantial over here on your right-hand side.
Okay, gotcha.
But I didn't see a huge shift for the maximum lifespan on your worm lifespan study. So along those lines, did you look for synergy with DAF2 mutant animals?
So two parts to the question. One, you're absolutely right. The increase in maximal lifespan is negligible compared to the effect on median lifespan. Because DAF2 attenuates insulin-like signaling, which terminates in DAF16, we don't expect synergy, but we haven't done it yet, so it could still be done.
Here. Your effects of aspirin on ROS and protein aggregates, you fit into sort of the insulin pathway, but have you actually checked if they're DAF16 dependent by doing those experiments in the mutant?
No, we have not. You're asking, have we done all the endpoints
in a
just
DAF16 maybe the
mutant?
ROS accumulation or protein accumulation?
Have not.
No.
It's a good idea. It need not follow the survival.
Right, just
quick question. Since you already did dose-dependent studies, maybe you tried intermittent feeding of, introduction of aspirin into medium? So
have we tried alternate day aspirin?
Yes.
No, we haven't. Okay. I don't think the worms get indigestion, but maybe they do.
It could have hormetic effects if it's FOXO and COX-2 inhibitors.
I'm sorry?
Well, since it acts on FOXO and COX2, it could have hormetic effect. It could be a hormetin. So that's why alternating could have an effect as well.
I'm not hearing the question very well, I'm sorry.
Aspirin could have hormetic effects. It could act as a hormetin.
Hormetic effect of aspirin in what respect?
Well, that's if it acts on FOXO and COX2, it could have positive effects if you induce pathways that act in response to stress and act for a little while.
Well, certainly, C. elegans has been an extremely strong supporter. Every one of them votes in favor of hormesis. Now, what I mean is that a lot of studies have been done showing hormetic effects that affect lifespan in C. elegans. So you're absolutely right that that's a possibility, but I have no data to address it.
And one quick question. So if you were to translate that to humans, which is close to impossible, what would be the recommended dosage to take?
Well, you said it yourself, and I said it earlier. It's impossible. You can't tell. All that we know from the Physician's Health Study and the other large clinical trials, which are the only things that should be used to guide human dose, are that low-dose aspirin is almost exactly the same in terms of its benefits as high-dose, 325 milligram every other day. And so either of those seems to work well. But none of those studies compared in one study a variety of dosings. So we don't really have that information.
Thank
you. Okay.
In any emergency rooms in the United States, if you come with chest pain, the dose is 81 milligrams sublingual.
Again, I'm not hearing very well. So.
In any emergency rooms in the United States, the dose on admission for rule-out MI is 81 milligrams. If you come with a stroke after a CT scan, which we will not show bleeding, the dose is 325 milligrams. These are studies which have been confirmed and reconfirmed. The common on Alzheimer's disease, it's very marginal. I don't know if you're familiar with the Rotterdam study on Alzheimer's disease, which has been shown that NSAID have been quite effective. It is not a prospective study. Aspirin was not shown to be of any benefits. But that's the clinical world, just to understand that there are standard doses which have been around for the last 15, 20 years. Thank you.
Just a brief response. The efficacy of aspirin in different studies has been controversial. It appears to be most indicated where the risk of cardiovascular event or whatever other disease you're looking at as an endpoint is the highest. And that's normal for studies because that's the subpopulation in which they have the greatest power to see an effect. I'm not sure there's a lesson you would want to take home about whether it's beneficial or not. I think that the fact that we have comparable effects in 3 different species tells you that something's happening. But I'm very loath to take the clinical data where sometimes they were significant and sometimes they weren't as indicating that you have to be over 65 to take aspirin. I think that that's just where the benefit is greatest.
Yes. Does aspirin affect chromosomal protein acetylation, at least in C. elegans?
Oh, that was actually another question, was about histone acetylation, and I neglected it. So among the proteins that aspirin is known to acetylate are histones, but I don't know whether that has any effect on chromatin structure, and that certainly hasn't been studied in C. elegans.
In one of your first slides, sorry. In one of your first slides, you showed a 7% increase in the lifespan of male mice. Is that the average of maximum lifespan? And in your final slide, you showed that aspirin has an effect on the lifespan of mice in general. Is that not a big step?
What was the last part?
The general conclusion you said it has effect on lifespan in general, on lifespan of mice in general. And you only showed the effect on lifespan of male mice.
Right. So that of course is not our work. That's Weindruck and Harrison et al. But that 3-site study only found a significant effect in male mice. There was an effect in female mice. It was clearly smaller and not significant. That doesn't mean that it wasn't a benefit to females. It does appear that the effect is stronger in males, and that's probably androgen related. Thank you.